welcome our next speaker, Dr. Shrey Sanadhya from University of Iowa. He will talk about co-boundaries of commuting Borel automorphisms.
First of all, I'm not a doctor yet.
Okay,
I'm
still
a PhD student.
Okay.
And I want to thank the organizers for giving me this opportunity to give a talk. Today, I will talk about co-boundaries of commuting Borel automorphism. So this talk is more on ergodic theory and dynamical systems, and in particular on Borel dynamics. And I will explain what Borel dynamics is. So we start with a theorem in ergodic theory, and this is a theorem of Kornfeld from 1999. If sigma and tau are two commuting invertible or ergodic measure preserving transformations of non-atomic probability space, then they have same set of co-boundaries or group of co-boundaries if and only if sigma is equal to tau to the power plus minus 1. And let me remind ourselves what ergodic means. A transformation tau is ergodic if for any measurable set A such that A is invariant under tau, then either the measure of A is 0 or the measure of A is the measure of the entire space. And the next thing we should talk about is what do I mean by co-boundaries? So of a transformation. So a measurable function f is called a co-boundary of a transformation tau if I can express f in this form, where g is another real valued measurable function. If I can do this, if I can write f like this, then I'll call f a co-boundary of tau. So I should mention that co-boundaries of a dynamical system are extremely important group of functions, and they have been extensively studied. And their property, they describe the property of the transformation. For example, if my transformation is measure preserving, then its co-boundary has integration 0. And for example, a constant function can never be a co-boundary except if it is 0 function. And the definition of co-boundary that I give here is in context with dynamical systems, but there is a relation to the cohomology that we study from algebraic topology. And if I have time later on, I can probably talk a little bit about the relation between this definition, which comes from dynamical systems, and the definitions of cohomology as we study in algebraic topology. So coming back to this theorem now, so it's a if and only if statement. And this direction, the backward direction is pretty obvious. And here I explain it. It's if I assume that sigma is tau inverse and f is a co-boundary of tau, then easily I can prove that f is also, I can write it like this, f is also a co-boundary of sigma. So this direction, the forward direction, is the most important one, and that's what Kornfeld proved. Okay. So there is a similar theorem in Cantor dynamics, and this theorem is from 2000 by Nicholas Orms. If xt and ys are two Cantor minimal systems, and I will explain what Cantor minimal systems are, there is an orbit equivalence, and I'll explain what orbit equivalence is, which induces a bijection from the set of real S coboundaries to the set of real T coboundaries, if and only if S and T are flip conjugates. So these are the 4 things that I underlined. I will explain what they are. So first, what is a Cantor dynamical system? So let X be a Cantor space, and by Cantor space, I just mean a 0-dimensional compact metric space with no isolated points. And T is a homeomorphism of X. Then we call xt a Cantor system. And if every T orbit, so this is one T orbit of X. If every T orbit is dense in X, then we call T to be minimal. Now the definition of orbit equivalence, if two Cantor systems xt and ys, we call them orbit equivalent if there exists a homeomorphism which takes the X orbit, the T orbit of X to the s orbit of hx. The other thing in the theorem is the bijection between the set of coboundaries. So how does that work is, if G is a coboundary of S and H is the orbit equivalence that we just talked about, then the push forward of G is a coboundary. If the push forward of G is the coboundary of T, and this map is a bijection, then we say that this H is inducing a bijection between the set of two coboundaries. The last thing in the theorem was conjugacy, flip conjugacy. So conjugacy is pretty straightforward. It's if x, t, and y are two systems, we say that they're conjugate if we can find a homeomorphism such that h of tx is equal to s of hx. And I should mention that conjugacy implies orbit equivalence, but the other way around is not true. We can say that S and T, we say S and T are flip conjugate if either S and T are conjugate or S and T inverse are conjugate. So with this all definitions that we have, let's go back to the theorem one more time. So what does this theorem say? This theorem says, we know that flip conjugacy always implies orbit equivalence. This theorem gives us a criterion when orbit equivalence implies flip conjugacy. And the criterion is that this orbit equivalence should induce a bijection between the set of S coboundaries and the set of T coboundaries. Okay. So the question is, can we have a similar result in Borel dynamics? And I'll explain what Borel dynamics is. So the answer is yes. And that's my main theorem. Before I explain what Borel dynamics is, let me explain one result, which is a very important result in measurable dynamics, and it's called Rocklin lemma, or sometimes Rocklin-Kakutani lemma, Kakutani-Rocklin lemma. Let T be a aperiodic, and by aperiodic I mean that the set of periodic points have measure 0. Let T be an aperiodic measure-preserving transformation of a probability space. Then for every natural number n and every epsilon greater than 0, I can find a measurable set A such that all these iterations of A are disjoint, are pairwise disjoint, and their union is almost the entire space X. In 72, Kohns and Carlston Weiss gave a ZD version of this Rocklin lemma. And here I have written just a Z2 version, just so that it's easy to write it down. So this G is a Z2 action, which is generated by these two commuting aperiodic measure preserving transformations of probability space. Then for every pair, like here we were working with just one natural number here for a pair NM, and for every epsilon greater than 0, I can find a measurable set A such that all these sets where I vary from 0 to n minus 1, J vary from 0 to m minus 1, the union is almost the entire space X. And why I am mentioning this theorem, the reason is that Kornfeld used the Z2 Rocklin lemma to prove his theorem, the theorem that I just discussed. So when I was trying to do this in Borel dynamics, I was thinking, can we find a Z2 Rocklin lemma or a ZD Rocklin lemma for Borel actions? And the answer is a partial yes. Partial yes. And I've explained, that's my second theorem. So now let me explain what Borel dynamics is. So in Borel dynamics, we work with a complete and separable metric space, X. This space is also sometimes called Polish space. And the pair XB is called a standard Borel space, where B is the sigma algebra generated by open sets. Let tau be, or let T be a one-to-one onto Borel map, then we call T a Borel automorphism of XB. And by aut XB, I denote the group of all Borel automorphisms of XB. And here we will only work with countable subgroups of aut XB. So I should mention, yeah, the next 2 points are very, very important. Borel dynamics is very different from measurable dynamics because we do not work with a reference measure. So if you remember, in measurable dynamics or in ergodic theory, we have x, mu, and t, where we always have a reference measure and we work up to that measure or almost everywhere. Here, our maps are defined everywhere rather than almost everywhere. So this is a step further than ergodic theory. And I should mention that a very nice introduction to Borel dynamics is given in a book by Professor Nadkarni. His book is called Basic Ergodic Theory, and it has a very good introduction to Borel dynamics. So let me describe one more definition, and then I can proceed to the theorems. A Borel complete section for a group gamma is a Borel set B such that when I act on B with gamma, I get the entire space. In other words, the saturation of B with respect to gamma gives me the entire space X. So my first theorem is that if S and T are two aperiodic, and here aperiodic means that every orbit is countable. We cannot have finite orbits. If S and T are two aperiodic commuting Borel automorphisms of a standard Borel
just
space.
a question. So orbits, so every orbit is countable, but do they have limit points or they are discrete set?
No, they're discrete.
I mean,
we are working with Z action.
Okay.
Right?
Okay.
Right.
No. I mean, there may be even if you take Z action, then there. I mean, it depends on the definition. You may have. I mean, so you are considering only discrete action.
Yes. Commuting Borel. So we have S and T, two aperiodic commuting Borel automorphisms of our standard Borel space. Then S and T have same set of Borel coboundaries, if and only if S is equal to T to the power plus minus 1. And here I should mention that these coboundaries are just Borel maps and they are defined everywhere, not almost everywhere, unlike in ergodic theory. The second theorem that I have is a weaker Rocklin lemma and ZD for ZD actions. So I have D. So these are finite number of aperiodic commuting Borel automorphisms, and gamma is the group generated by these automorphisms. So it's a ZD action. And we also assume that gamma acts freely. What does that mean? That just means that if for any x, gamma I x is equal to x, this implies that gamma I is identity. Then for any D tuple, like in Z2 case, we were taking the pair here we are ZD. So for any D tuple, we can find a complete section A such that all these sets are pairwise disjoint. And why I am calling this a weaker form, because I'm not able to cover the entire space. So it's a weaker form of Rocklin lemma. And I should also mention the Z version of this Rocklin lemma was given by Benji Weiss, I think in 80. I have to check that. Okay. So in the rest of the time, I think I have like 3 minutes. I'll try to give a sketch of the proof of theorem 1. So if you remember, this direction was obvious. So this is the only direction that we care about. So that's what we have to show. If coboundary, the set of coboundary of S is equal to set of coboundary of T, then we have to prove S is equal to T to the power plus minus 1. And it's enough to show, you can check real quick that it's enough to show this. Now, we will prove this by contrapositive. So I assume that S is not a power of T to T, and we will find a function F such that F is a coboundary of S and but F is not a coboundary of T. So the whole, in this whole proof, I just have to find this function f. F should have following two properties. The first property is that if the composition of f with power of s and the absolute value of it should be bounded above. And if you recall, people who do dynamical system recall that this is Gauss-Headland theorem. This is the version of Gauss-Headland theorem. So this A will give me that f is a co-boundary of s. And we are kind of using the reverse of Gauss-Headland theorem. And we will say that if the absolute value of this f with the powers of t is bounded below, then it will imply that f is not a co-boundary of t. So A will give me that f is a co-boundary of s, and B will give me that f is not a co-boundary of t. I should mention that I'm using this mu here, and this mu is gamma quasi-invariant. By quasi-invariant, I mean that it preserves the zero measure sets. So the whole theorem, whole proof is now focused on finding this f with these two properties. And that's where I will use the Rocklin lemma, which is the theorem 2 that I proved. And we will work with Rocklin towers, chi-r, which is generated by the Z2 actions of S and T. So this is a Z2 tower, and this direction is S, and this direction is T. And what I mean by that, this direction is S, I mean, if this is the set AR, then this is S of AR, this is S square of AR, and so forth. And this is T of AR, this is T square of AR, this is ST of AR, this is S square T of AR, and so forth. Okay? And I have defined FR to be 0 outside this tower. So this tower is of size NR times MR. So this size is NR, this size is MR. And I've defined FR to be 0 outside, and inside the tower, these are the values of FR. So in this block, the value is 1.25 AR, and then it alternates to minus 1.25 alpha R, and so forth. And here it's 0.75 alpha R, then minus 0.75 alpha R. So when I've cleverly chosen this value of FR, if you see that in this direction, it is bounded above. And in this direction, this value of FR is bounded below. So this will, with some work, this will give me A, this will give me B. And that's how I will prove my theorem. And that's all I need for my function to have these two properties, and then I'll be done. So that's all I have. And I have the preprint available. Thank you for your time.
Can I ask a question?
Sure.
Yeah, this is Riddhi Shah. I just wanted to know, when you took this cross section, Borel cross section, that B, those are not disjoint sets, right? This B.
Those are not required.
And B is just a Borel set, not open or anything.
It's just a Borel set, and it's not even a transversal. So it's a set in which every orbit has to pass at least once.
But then you could also just have B equal to X, right? I mean.
Yes. Yeah. Yeah.
So you have to basically choose B, which will help you, is it?
Yes.
I also wanted to. Sorry. Go ahead.
So they exist. For example, pick one point from every orbit. Okay, you have a set, and now just make this set thick enough so that it's a Borel set.
Okay.
And you have a complete section. And in case, for example, if you study substitutional dynamical systems, then every cylinder set, if you look from this perspective, is a Borel complete section.
So I want to ask you one more question. You know, when you say discrete, did you mean every orbit is discrete, or what did you mean discrete in that sense?
I just mean that they do not tend to just one point, and they do not like stop somewhere. The orbit has to be
no, but even if it is
infinite.
even if it is infinite, it could still have a limit point, right?
I don't think we need. That's all I need. I need that the orbit
they are
is
just
countable.
countably infinite. That's all you
That's
need.
all I
so
need.
orbit is
Yes.
infinite. That's all. But limit points could
That's
be
all.
there, so that is not a problem.
Okay.
So it's not
Okay.
discrete really. Okay, thank
Okay.
you. Very nice talk.
Okay.
I have a question.
Sure.
Yeah. So one of the kind of a naive question. So if two things has the same co-boundaries, what are the implications that we can have about those? So having equal co-boundary give you some extra information. What kind of extra information do we get?
That's exactly what we have proved. If you look at the theorem, the first theorem of Kornfeld.
Yeah, exactly.
If these two sigma and tau have same set of co-boundaries, then they are completely determined. We know everything about them.
Yeah, okay.
So they can either be equal or inverse of each other.
Yeah, but you also have kind of a assumption starts with a commuting pair, right?
Yes.
So that's what my question is.
Yes.
Can I have some extra information if they're non-commuting?
No. Okay. Like I wanted to try this work in non-commuting, and I was not able to proceed. It was
Maybe
hard.
you can start with some examples and see how it goes, because to get same co-boundary it's not easy, I think. So
yes.
I'm just guessing.
Can I ask?
Sure.
What is the role of non-atomic here?
Oh, we just want to want to
yeah, but I mean, where do you use non-atomicity?
So my theorem is in Borel context. I do not even need any measure.
Oh, I see. Because if you want to know atomic measures whose range is an interval, there are many.
See this theorem which Kornfeld proved is in measurable dynamics. So he is concerned about measures. I am
total measure is one, that is fine. But the values that the measures take on the Borel algebra, those values form an interval for many atomic measures also.
I do.
And I can tell you binary sequence 1 by 2 raised to n sitting at n, its range is an interval. If you take discrete space, okay? Its range is an interval. And there are many sequences, they are called interval filling sequences. But I'm telling you, this is, okay. Okay, so there is a paper by Ribbenbaum in 1984-85 telling about reciprocals of Fibonacci sequences, and the idea started with Kakeya long time ago, about 100 years ago. And if you want to look at literature, you can look at my paper with Lalton Puya in Journal Convex Analysis 2008.
Maybe I can email you and
up to you. Journal Convex Analysis 2008.
Thank you.
If you email me, I will send you a talk which tells all about that.
So is this published somewhere?
It's on archive right now. I have submitted it. it.
Okay. Interesting. Thank you.
Okay. So let's thank the speaker.